So, to start with this topic, let us recall the concept of limits, continuity, and the differentiation for one variable case. When you have a function of only one variable, one is dependent variable, another is independent variable. Now, if you look at the function, that area, so area is a function of length and breadth. So, it depends on, for example, if you say A, area, it is a function of x and y. So there are two independent variables. Yes, it is on record. Yeah, it is. It is being recorded. I'll share the recording also. Don't worry, because this Google Meet has disabled the recording option, but I am recording with some other software. Okay, so you don't worry about it. Yeah. Now, if you have the volume, so volume of a parallelepiped, for example, if you have a parallelepiped of this kind or a rectangular shape okay, so the volume will depend on the length. This is the height, you can say length, and the breadth. So x, y, and it. So there are functions. Volume is a function which depends on three independent variables. In fact, in real life, most of the functions are several variables. Mathematically, we study, because this is the simple case, only one independent variable and one dependent variable. Okay. But if you look at the engineering problems or real life problems, you will get most of the problems are actually several variable problems. The function here, for example, the height. Suppose you want to do the trekking, climb climb the mountain, and you want to go to the top. So, which direction should be the shortest path or the fastest route? That will, whether you start from there or this. In fact, this can be one route. There are maybe you cannot. There are, in fact, if you have visited any mountain or hill area, then you have seen that the road are not straight lines. Okay, they will be like this kind of like roads. Similarly, what would be the shortest path or shortest route to reach the minimum point of a valley? Okay, whether you will reach this is the fastest way or this is the fastest or this one is the fastest way. Now all this, both of the case, whether you reach to the maximum point or the minimum point. Okay, in fact, if you try to get this point, so it will have x, y, and z. From this coordinate, you will go x direction, then y direction, and then also height also will be there. Now let us recall the slope of a tangent, or we will try to define the slope. So if you try to climb up the hill area, okay, or if you run, then how much you are actually rising. So from this point you go to up to this point. Okay, the rise will be 20 meters, but you are traveling 5 5,000 meter. Okay, so this is a slope is very less. Okay. In fact, to understand the slope is actually rise over run. Now same thing, that means you are going in this direction. Okay, you are rising. So similarly, negative rise, that means you are slope, you are sliding. sliding down. So if you go this direction, then how much change is depending. So this is the delta x direction, and this would be the delta y direction. Now, why this is important? Because look at the problem. You want to go up or you want to go down. So, which would be the shortest route? So that is, so there are only two types of slopes. Either one would be positive slope going up, another would be negative slope. Now, how this is related to the derivatives? Now you have to understand. For example, the derivative of a function, if you try to define, so we have seen the one variable differentiation from one variable calculus. The ordinary derivative, okay, is defined by this way. So if you try to look at the diagram here, just look at the diagram here. It says that this black dot point is a, for example, x is a particular point where you want to calculate the derivative. Okay? And what it means, the red point is moving along the curve. So whenever it goes up, so that means it is going up means rising up or going down. At the same time, what will be the value that h goes to 0? The value of h. Now, if you try to move the black point also, then together they will move. So when h equals to 0. Now, if you try to change the value of h from 2 to minus 2 to 2. Okay, so what happens here is actually, so this is the delta x direction actually. For example, this is x1, this is x2. And when the red point is here, okay, then what happens? This is delta x direction. As delta x goes to 0, then we try to calculate the rate of change. You remember the rate of change of y with respect to x. So this is the reason that we are allowing h goes to 0. So whenever you move here, so from 2 to minus 2, okay, if you change these values, then we can see that the derivative, the limit, the limit is actually equal to the at this point the functional value at this point. Yeah. So just to recall, if you try to, yeah, here it is. When we are increasing, where we are moving from this to this, h equals to 0 here. If you try to move up, then the red point, here it is actually going to the, going towards the, this black point here, the black dot point here. To understand the formula of a derivative, so that means this is rising, okay, over the run. If you run in this way and if you rise in this direction, if you run, okay, this is the rise and here it is the run. Now this is for one variable case. Now what will happen? Also you have to know that when the derivative is negative, then it is going down. When the derivative is positive, then it is going up. For example, if you look at here the video, so the red point is actually moving up when, and also you change the rate of change, the derivative th with respect to t. So this is a temperature function with respect to height. Okay. So this derivative is actually moving up when it is positive. It is positive. Sometimes it is negative also. So it is negative and positive also. So rate of change will be positive and negative. and the tangent will move its direction constantly if you change the point. When it is 0, the tangent is, I mean, the derivative is 0, then this will be parallel. Okay. Now the same thing, you want to generalize the concept if we have a two variable function. For example, this is z is a function of x and y. So this is a surface. It represents a surface. Now if you try to find out the change, for example here dz dx, if you try to define, it is not possible to define because it has another independent variable. So for this type of function we have to define, it's called partial derivatives. So partial derivatives, what we will do is actually we will try to find out first with respect to x, and then there will be another derivative. For example, it will be in this direction, okay, and the tangent will be of this form. Tangent will be of this form. So this is the tangent over this curve, blue curve. So another derivative will be del f, del y, and xy with respect to y. Now, if you look at this function, because it is this function f is dependent on two variables x and y. Okay, this is, so here we will define these notations actually. Dou x, dou f, dou x, and dou f, dou y. So two in different. So say, for ordinary derivative, we will use the notation d. And dou will be denoted for partial derivatives. So we'll formally define what is partial derivatives, but we have to understand the geometry, what it means actually. Okay. Now, if you look at the diagram, if you change the point, if any point, this black point is moving here, what happens? This is changing x direction. At the same time, it is changing the y direction also. Y value also changes. So that is why we have to mention that which direction you are actually mentioning with respect to x or with respect to y. You cannot do at the same both at the same time. One after another can be there. You go in this direction and then here. Okay, rate of change we will calculate at the same time, but the point will be changing constantly. Y value and x value will change constantly. Okay, so if you just look at the diagram here, what happens? Yeah. So if you change it with respect to x direction, actually, here you can see it is only for x direction. So for x direction, you can see that the function, the rate of change is positive. Sometimes it is becoming negative, and also sometimes become 0. It will become sometimes 0 when it is parallel to the x-axis. Okay, so the rate of change here you can see. You can see here the rate of change is positive and negative also happening. Same idea. Now, if you generalize this concept, so if you look at, so there is a function, h is a function here, h is a function of h of t and I. So here you calculate dh, dou h, dou t, and dou h and dou I. So this is, so what will be the tangents? So for example, you have this kind of another tangent will be there. So this figure you can see here, the diagram. Now if you move the point, the black dot point, if you move this, then you can see that there is a change. So both the derivative will change simultaneously, but we have to calculate with respect to one direction at a time. Okay, try to look at the values here. X value, Y value changes. At the same time, the rate of change also changes. If you move it, then you can see that there is a change. See, X and Y constantly changes. And say at the same time, due to this change, the rate of change also here also. So this is our X value, this is our Y value. So these values are changing at the same time. The rate of change, the partial derivative at that particular point also changes. So the rate here it is, if you remember, the slope will be of this form. It will change its directions. That means if you move in the mountain or in the valley, so what will be the changes? So this height will be there will be del h del x del h del x del y and then del h del z. So these functions will be there. In fact, you can call it as a function of 2 actually. At any point, surface z equals to f of here it is z equals to this particular point can be defined as x and y, h of x and y. Similarly, you can go down this valley. So this valley, the minimum point you can find v of x and y. So there you will try to find out dv, dx and dv, dy. So if you move along this direction, then the tangent that you are having. So x direction how much changing, y direction how much changing. So that okay. So in this way you can go to the minimum point. So this is the basic idea of partial derivatives and why they are needed in order to change, in order to see the rate of change when we calculate with respect to x and with respect to y. And they will be useful for finding the uh, minimum point, maximum point of a given function. Okay. So let us formally define the function of several variables. As we have mentioned already, if you think of a parallelepiped, then the volume is actually x, y, and h. Depends on the three variables. So x is the length, y is the breadth, and h is the height. Now z is called the function of two variables if it depends on x and y. For example, area. You have seen area is a two variable function. So symbolically we will try to write down z equals to f of xy. Now that's geometrical meaning of f of xy. So this is geometrical. Geometrically it will represent a surface of this form in the three-dimensional phase. So similarly, if you try to think of this function, okay, z, it can be function of x or it can be function of x1. Z can be function of f of x1 and x2. Two variable. We can have three variable. We can have n variable also. So there are several variable functions up there. Now, as you know that for a function, what we do from one domain to another domain, it will represent It will associate the members of here with the members of this cell. So domain and a codomain. Okay. So what will be the limit for a function of several variable? You need to define the limit because you want to define the derivative. Okay. So here you have to define the limit. So if the function is a two variable function, several variable, two variable function, then what happens if you take a comma b at a point, that means it has x direction, it has y direction. Now we can reach to a by any direction. Okay, you can reach in this direction, you can reach in this direction, or you can reach in this direction also. So all possible direction can be possible. Either this way, or you can go this way. In fact, you can go in this way also. This is also possible to reach the point. But if you remember the definition of when we have y equals to f of x, the limit what we have defined. So this will be a function like this, and we have taken the right hand limit and the left hand limit, L plus and L minus. When they are equal, we have said that the limit exists. But here we don't have this much actually. Here you can move. There is no right hand or left hand limit. It can be maximum number of, in fact, infinite number of possibilities are there. Infinite number of paths are there to reach any point. So that is why we define the function, the limit in a different way. So x tends to a and y tends to b. Okay, if there is a finite number L, if the limit is independent of any path followed, so you can follow any path you follow, and if the functional value is L, then we call this L is the limit of this function. Earlier case, what we have discussed, when the left hand side limit and right hand side limit are equal and they exist, then we call that L is the limit of the function at that point. But here there is no L or left hand or right hand. Here it can be many possible ways to go there. So in other words, the function fxy in the region R is said to be tending to its limit L as x tends to a and y tends to b if the corresponding to every corresponding to every epsilon greater than 0, there must be this should satisfy this relation. So what it means, we will explain it with an example. Okay, so this is our function z equals to f of x comma y. Okay, this represents the surface. So here we have one point x naught, y naught and 0. Since this is on the xy plane, so z equals to 0 here. So this is the point we have calculated. Now, for example, L is the z equals to L here. Okay. We are claiming that L is the limit of this function. As so, you can go x tends to x naught and y tends to y naught, x naught and y naught. Then you will get the limit as L. Here it is. This L will be the limit. The meaning is that if xy not equals to x naught y naught, and if the disk, here it is, the disk you can see here. So this is the disk. This is open. What is open and closed we'll discuss later also. Okay. So this is nothing but when we have an one variable case. So x plus a, or let us write x plus epsilon and x minus epsilon. So this is our open interval. But when we have two-dimensional shape in this figure, okay, then if you try to define x naught y naught, and if you try to define in this way, so that is a equation of disk actually. So this is a disk, that means considering all the points. So x goes to x naught at any direction and y goes to y naught at any direction. Okay. Then the functional value will be at L. If this satisfied, then what happens? All the functional value, that is L, the difference between, so this is the L value. And what is f of xy? This is our f of xy here. Z equals to f of xy. Okay, so if it is the limit, then it is saying that the difference between the functional value and the that is the point L is less than epsilon for any given epsilon equals greater than 0, and satisfying that, they will satisfy the relation, this one, that x, that is x minus x naught whole square plus y minus y naught whole square less than some delta, and this delta is dependent on epsilon. And this is greater than 0. So this will satisfy. In fact, if I give you one example, then it will be much more clear. Okay. So for example, if you take this function f of xy equals to this one, then if you put 0 0 here, then what it becomes? So 0 by 0 something, okay, which is undefined. But we are claiming that 0 is the limit. That means if f of L equals to 0 here, so you have to show that f of x minus y minus L less than some epsilon for given for some yeah, this x minus 0 square plus y minus 0 square less than delta. Okay. So this is our aim actually to show it. So let us try to investigate what is the uh, difference. What is the definition of the limit? So f of x y is 5 times x square y square divided by x square plus y square. Now our aim is to define limit uh, xy goes to 0 comma 0. So that is f of x y. Try to find out what are the planes. So this is our actually maybe the task. Okay. Trying to find out the limit of this function. Okay, the claim is the f of x comma y goes to 0 as x comma y become close approaches to 0 comma 0. So here what we do, suppose we will take epsilon greater than 0, then we will try to look at, in fact, so L is actually, this is our L. Okay, 0 is our limit. This is our claim. So f of x minus y minus L is 5 x square y square minus x divided by x square y square minus L minus 0. Okay, so this is nothing but 5x square y square by x square plus y square. Okay, now what is our delta? Because we need to satisfy that from here x minus 0 whole square plus y minus 0 whole square, that should be less than delta square. So this is nothing but x square plus y square less than delta square. Now suppose, remember we have said that this delta depends on epsilon. So let us choose delta equals to epsilon by 5. Then what will happen? So delta square equals to epsilon by 5. Okay. Now we have f of x minus y minus 0, which is 5 times x square plus y square, sorry, x square times y square divided by x square plus y square. Okay. Now can we claim that this is so from here we have In fact, you can write it here in this. So 5 can take, you can take out x square plus y square divided by x square plus y square. Now this is our claim that this is less than epsilon. So here you get pi delta square equals to epsilon. Okay. 5 y square. Let me just divide it by x square plus y square. Let me plot the graph, then I will tell you what it is actually happening. So here, yeah. So from the previous relation, we have to show this one. Okay, this depends. Suppose we choose this epsilon greater than delta square. Then what happens? Let us try to find out the value of this quantity. So since this is x square plus y square, for example, if you take x square, let me 1 times 2, then 1 square plus 2 square. So what is the value? Is it less than 1? So x square plus y square, or you can write x square y square less than x square plus y square. Then you can satisfy this x square y square divided by x square plus y square, which is less than 1. Okay. So if you can just take that delta square, if you define this is epsilon by 5, then what is happening? So let us just take x square, or let us take x square, or 5 x square outside. You can take x also outside. Okay. So this is, now if you have this one, so from there you can write y square. This is a positive quantity. Okay. And you can write here, this is delta square. This is also satisfied. Now if you, in place of this y square, you can write delta square. Okay. And then for this one, you can substitute. Yes, yes, just a minute. Now for a b, we can write a dot b. Okay. So from here we can write this. So this is also positive quantity. This is also positive. So this is, we can write it. Okay. Now let me just show you here. So we want to show this one. We want to show f of x minus y less than 0 is less than epsilon. Okay, this is our game. So for that, so far what we have, this one, and we can write this quantity is less than this one. This is a, you can call it b. So it satisfies this relation. Now I am telling you that, so this is true. This relation is true because we are adding some more value. Okay, you can write it in this way also. If both are 0, then it will be equality. 0 less than 0, that is going to be absurd. So our aim is to make it as less than 1. So x square by x square plus y square is less than 1. We can make it. So if you multiply by 5, then this will be 5 times will be multiplied 1. Now this quantity, what you can see, and we have here this one. So y square is less than delta square. So for this, so y square, we can substitute delta square. And for the other part, what you can write? You can write 5 because this part is less than 5. So you multiply 5. In place of delta square, we can now write epsilon by 5, and this is 5. So 5 gets cancelled, it becomes epsilon. So let me just refresh again. Okay. So the aim is to f of x y minus L. If remember, if L is the limit of f of x y at x naught y naught, okay, or okay, let us say at a comma b, then by the definition f of x minus y minus L will be less than equals to 0, then okay, for every epsilon greater than 0 there exists a delta, okay, depends depends on epsilon such that such that f of x minus y, sorry, f of x comma y minus L less than epsilon whenever this one, what is it, yeah, x minus a square plus y minus b square less than delta square. So whenever this is true, this will happen. So for this particular example, let us see what we are seeing actually. In fact, if you remember the definition of limit y goes to, sorry, x goes to some point, x goes to a, fx equals to L. What was the meaning? So here the meaning was fx goes to L as x goes to a. That means the difference between the fx and L was less than epsilon whenever the difference between x minus a less than delta. In other words, so this is our fx and this is our x. So this is, for example, x equals to a. Now this is the meaning is x minus delta a minus delta x less than a plus delta. I can write it. Okay. So here it is. What is happening? A minus delta. This is x. Sorry, this is a. Let us a plus delta. Okay, this is x value. X value changes. X1, x2, dot, dot, dot. When x a equals to x, then what happens? The limit of the value. Okay, if we say the limit, so it says. So for this, what we can write? L minus epsilon less than fx less than fx. So L plus epsilon. L plus epsilon. So what happens? The functional value at this point, so this is fx at a, at x equals to a, will be, this is L plus epsilon and this would be L minus epsilon. So you take this point here. Okay. So for any given point, if you take the left hand side limit or right hand side limit, you the functional value will be at this point actually within this limit. Okay, so this is the range of the fx. So L plus epsilon and L plus. So this is fx. In one variable case, if you remember the definition was meaning. Now, if you juxtapose the situation in the three-dimensional case, yes, tell me. Constant function is limits is everything, no? At any point, it is the limit for constant function. The functional value, for example, f of you're talking about functional value. F of x equals to some 2, for example, 2 is a constant. At any point, it will be 2. You give here f of 1, it is 2, f of 2, it is again 2. It is always the same value. So every point will be the limit point. Now, if you have a case of this is very important, you need to clarify the definition. Okay. So for constant function, in fact, mathematically you can define, but if you try to plot it in geometrical situation, then you may get some difficulties. For example, I'll tell you y equals to f of x equals say 2, right? Okay, so this is 2. Y equals to 2. For example, you take x equals to 2, no? For example, x equals to 3. Okay, and you take here this is 2.5 and here it is 3.5. In between 3 is there. Okay, take the interval. So what is f of 2.5? It is 2. F of 3, it is again 2. F of 3.5, what is it? Again 2. Okay. Now the claim is okay. L equals to 2 is the limit. That means you want to say fx minus L less than epsilon for epsilon greater than 0 whenever x minus uh, this is x equals to 3, right? X minus 3 less than some delta. Okay, for this example, let us try to verify. So the claim is L equals to 2 is the limit. So here you can see for a given, you are assuming, or we have to assume epsilon greater than 0. Okay, now you have f of x equals to 2 and L equals to 2 also. So if you write here f of x minus L, so this is going to be 2 minus 2. It is always satisfying, no? This is 0. And you have by assumption, you can say here, it is epsilon less than epsilon. Whatever may be the point delta value, delta you can take epsilon by some 5 or some whatever may be. So for constant function, the functional value, whatever the functional value at that point is actually the limit point. Is your doubt clear? Okay. Now, if you have a different case, for example, here it is three-dimensional case. Okay, we want to calculate, that is a comma b. Okay, so this is we are telling that a comma b comma l is the limit point. Okay, but like I said that for two-dimensional case, you can go either left from the left side or the right side. Okay, so that is why we have taken the absolute value, only the absolute value. But when it comes to two-dimensional case, then we have to take all the directions. That means we have to take this value, or if you uh, that means we have to take all the directions. Yeah. So this is our direction, all the direction. So if you consider all the directions, so that is why we have to mention that x minus a whole square plus y minus b whole square less than delta square. So if this is satisfied, then this must also satisfied. Only then we can say that is the limit. If we can satisfy this relation, then whenever we have this relation, then only we can say that this is the limit. Now to verify, for this example, we have seen that if f of x y equals to 5x square plus y square by x, sorry, 5x square into y square, x square plus y square, we have said that this goes to 0 at 0 comma 0 as x comma y goes to 0 comma 0. That means if you take, for example, epsilon equals to half, then it is greater than 0, because our target is to, if you select for every epsilon greater than 0, so that is why let us take any half, epsilon equals to half. Then we have seen that delta square equals to, we have selected epsilon by 5, so then it will be half by 5, so that is 1 by 10. Okay, so that's how you can select it. But if you try to look uh, at 0 0, so what it means actually, at 0 0 point near, okay, let me just show you the graph of this point. Actually, the graph of the function will be look like of this form. So this is, let us from the top view, let us take another from bottom view. So this is the function of actually from top. Okay, so from if you look at the function from the top, then you see here the functional value at 0 0 it matches. Actually, you can see this matches at 0. But if you substitute the value 0 0, then this is not going to. Then this is going to be infinity. Sorry, 0 by 0 form, infinity form, or undefined form. So that is why if you this function is not defined at the point 0 0, but it is its limit point is here. 0 0 is a limit point, that it is the function is approaching to 0 0, but it is not matching. Similar to the concept of asymptote, they may look like, okay, they may look like intersecting each other, but if you zoom, they will not intersect at each other. So this function is not defined at 0 0, but 0 point is the limit for this function. Okay, so yeah, that's the geometrical interpretation for this limit function. In fact, Monday we'll look at some more examples and try to start from here. I'll stop here today. If you have any doubt, you can ask me.